Hello, my name is Dr. Jonathan McKendry, and in this presentation I will cover our recent work in the use of ultraviolet micro-LEDs for satellite quantum key distribution. And this is work that's been done in collaboration with colleagues at the University of Bristol and the Department of Physics at the University of Strathclyde in Glasgow. Here's a short overview of my presentation. First of all, I'll discuss satellite-to-satellite quantum key distribution, and in particular why we're interested in using UV LEDs for this purpose. I'll introduce the specific format of micro-LEDs that will be used in this work. Then I'll introduce the BB84 QKD protocol that was being proposed for this work, discuss how the micro-LED design has to be tailored to fit the requirements of this protocol. I'll show the micro-LED design and its characteristics, provide some preliminary results, and then a short summary and outlook for future work. Quantum key distribution is an inherently secure method of exchanging keys that can be used to securely encrypt and decrypt sensitive information. It has been shown that QKD keys can be exchanged over optical fibers at distances up to about 100 kilometers, beyond which it becomes very difficult due to the exponential losses in the fibers. So as an alternative approach, it has been proposed that satellite-to-satellite networks could be used instead, and even very small satellites, so CubeSats with dimensions of the order of tens of centimeters. So the use of ultraviolet light to transmit the information is particularly appealing for several reasons. So the ultraviolet C part of the spectrum, around 200 to 280 nanometers, is solar blind, meaning it's robust against ground-based interception because the light can't reach the Earth's surface. The shorter wavelength allows for smaller optics to be used, which is particularly important on CubeSats where size, weight and power is very limited. Similarly, using LEDs instead of lasers can further reduce the swap requirements. LEDs have better temperature stability, so there's less spectral and temporal variation and drift, which means that they're less likely to accidentally leak information from the secure quantum key exchange. And finally, there's a lower background noise in the UVC, so there's less solar spectrum to compete against in the UVC part of the spectrum versus the visible and the infrared. The specific format of device that we will show in this work are micro-LEDs. So micro-LEDs are LEDs with dimensions with 100 microns or less. We have found through previous research that the small dimensions leads to a smaller RC time constant, and the modulation bandwidth is then dominated by the much faster carryover combination process. This means that micro-LEDs can achieve bandwidths on the order of hundreds of megahertz, perhaps even up towards 1 gigahertz, compared to normal LEDs, which will have bandwidths on the order of tens of megahertz. Their format also lends themselves very well to be integrated with drive electronics. So figures B and C are showing how individual micro-LEDs can be directly bonded to CMOS electronic drivers, and that allows for the output patterns and the temporal patterns for hundreds, thousands, or even tens of thousands of micro-LEDs to be controlled through a convenient electronic interface. Here I present a short and simplified overview of the BB84 QKD protocol that is used in this work. So Alice at the transmitter will send photons to Bob at the receiver. Alice will choose either horizontal or vertical polarization to represent the zeros and ones, or a diagonal and anti-diagonal polarization basis. Bob will not know what basis Alice has been using, so he will randomly choose which basis to use for each received photon. Afterwards, once the exchange of information is complete, Alice and Bob will compare the bases that they used, and they will keep only the bits where their bases matched. So that's highlighted in yellow on the table on the right. The leftover bits shown on the bottom row is the derived quantum key, and that's the key that they would use to encode and decode their secure information. So the inherent security from this protocol comes from the quantum nature of the transmission. So if an eavesdropper has been intercepting the photons, then that will induce errors in Bob's quantum key. So if Alice and Bob compare a short section of their quantum key, If there are no errors, then they know that the information has been exchanged securely and no one has intercepted it. If there are too many errors, that indicates that their eavesdropping has taken place and they know that the information exchange has not been done securely. And that's the key differentiation from exchanging keys using a classical channel. In this slide, I'll discuss how we design the QKD system and the micro-LED array in order to meet the requirements for the BB84 protocol. So the diagram is shown on the right. You can see there's a micro-LED array which will transmit light from different areas on the array. These will then map onto various polarizers using some projection optics, and the polarizers will then output the different polarization states that are used for the QKD, so the horizontal, vertical, diagonal or anti-diagonal HVDA polarization states. These then map onto a spatial mode filter to make them indistinguishable from each other. Then they will be coupled to a fiber to attenuate the signal so that the mean number of photons per pulse transmitted is on average less than 1 photon per pulse. So what we require from the micro-LED arrays in order to meet these system requirements, first of all, we want to match the polarizer geometry, so we don't want optical crosstalk from one micro-LED polarizer channel to the next. We want to be able to exchange the QKD information as quickly as possible, so we want to be able to pulse the LEDs as quickly as possible, so we're targeting optical pulses on the order of nanoseconds. We want to be able to individually switch the micro-LEDs on and off in order to address a single HVDA state at any given time. And finally, we also want to vary the intensity of the pulses that are sent by the micro-LEDs. So sometimes we want to send a signal pulse to represent the QKD, but we also want to send pulses with varying intensity, which are called decoy states. Those decoy states are there to add further protection against hacking and eavesdropping attacks. This slide summarizes the resulting micro-LED array design that was used in this work. So the nominal peak emission wavelength from the devices is 280 nanometers. There are 8 identical micro-LEDs in the array. They're shown clearly in figure C. They're these wedge-shaped parts of the array. They're arranged in a quadrant, so around a circle, so that each quadrant, so the HV, A or D quadrant, maps onto one of the polarizers to give you your HVDA polarization states. Various micro-LEDs share a common anode, so for example H1 and V1 share a common anode, but every single LED has its own individual cathode. So by applying different voltages to the different anodes and by switching the different cathodes on and off, we can select which quadrant is active, so which polarization state is active, and we can also switch between the different signal and decoy states as required. This slide shows some of the characteristics of some of the as fabricated devices that were made for this work. On the left, you can see the current versus voltage characteristic for a representative micro-LED pixel, and we can see that we need up to 10 volts in order to forward bias the pixels. I'll talk about the implications of that on the next slide. On the right-hand side, you can see the electroluminescence spectra for a single pixel as a function of temperature, so measured at 20 degrees and at 80 degrees. We observed a shift in the peak wavelength of less than 0.5 nanometers, showing that the LED's spectral output is very stable with temperature, which, as I mentioned earlier, is very important for relaxing the optical design constraints and for making sure that the system is stable with temperature. So as I mentioned on the previous slide, we need a relatively high forward voltage to drive the micro-LEDs up to about 10 volts. However, we want to be able to interface them with the standard electronic signals that you would find on like an onboard computer that you might have on a CubeSat, for example. So in order to interface between these two, we use transistors. So the LED's anode is connected to a high voltage up to 10 volts, which is LED VDD in that diagram. The cathode's connected to the transistor, and then the transistors are switched on and off by a standard digital input signal of 0 to 3.3 volts. The test PCB that we designed and provided to our colleagues in Bristol for the QKD system is shown on the right. So the PCB is about 70 by 85 millimeters. The micro LED array would be wire bonded to the small aperture in the center of the board, as you can see. The coaxial connectors provide the digital inputs, which in our experiments would come from a waveform generator. And then there are 4 different voltage supplies that can be provided to the array in order to configure the different signal and decoy states. This slide shows some of our preliminary results. So here we are showing the pulsing of the micro LEDs. So as I mentioned earlier, we want to be able to pulse the LEDs on and off as rapidly as possible so that we can exchange the QKD information as rapidly as possible. Here the LEDs are being electrically pulsed using nanosecond or sub-nanosecond electrical inputs, and then the corresponding optical signals are being measured using time-correlated single photon counting. So when we interface with the LEDs through the transistors on the test PCB that I showed you on the previous slide, we were able to obtain pulses with widths of about 2.7 nanoseconds. We did test driving the LEDs directly, so essentially bypassing the transistor and pulsing the LEDs directly with a high voltage signal, and we were able to obtain pulses on the order of about 700 picoseconds. So that indicates that the drive electronics that we have at the moment are limiting how short we can make the optical pulses, so there are some improvements that could be done in future in that respect. So here's a short summary of this presentation and an outlook towards future work. So here we've demonstrated the design of a VVC micro LED array that is compatible with a concept BB84 QKD system. We've demonstrated that the pixels can be individually addressed in order to deliver different output polarization states, and that nanosecond or even sub-nanosecond optical pulsing is possible. Future improvements, we will look to do some direct integration with micro-optics to further reduce the size, weight and power, so to replace the bulk projecting optics with much smaller micro-optics. We'll look at faster drive electronics with a smaller footprint to make the LED array pulse faster and also further reduce the swap. And then we'll also be looking at emitting at different wavelengths, so looking at micro LEDs with emissions perhaps as short as 255 or 235 nanometers, where there may be some advantages going to shorter wavelengths. So for example, even further reduction in the solar background at those wavelengths. And then finally, and obviously we will look to do a full QKD transmission demonstration using these UVC micro LEDs. Finally, I would like to take time to thank our funders at the UK Space Agency, Innovate UK and the Engineering and Physical Sciences Research Council.